Beneath the thick ice of Antarctica lies a vast continent, the size of Australia, which remains a mystery to humanity. This hidden world spans an area of around 14 million square kilometers and includes mountain ranges reaching heights of 3,000 meters, deep valleys and plains that may once have been covered in dense forests. If we could remove the ice cover, we would be confronted with stark landscapes. Dark rocks protruding from the ice, bright white plains glistening under the sun, and winding riverbeds frozen in time as if waiting for their moment. These rivers might once have teemed with life, their waters reflecting the blue skies and white clouds. Notably, recent research conducted in 2017 by scientists from the University of California revealed the existence of underground lakes containing pure fresh water, as well as unique ecosystems that could thrive in conditions far removed from our own. These bodies of water, located up to 1 kilometer beneath the ice, may harbor organisms adapted to extreme conditions. For instance, in Lake Vostok, the largest subglacial lake, scientists discovered microorganisms that can survive without sunlight, using chemical reactions to obtain energy. 80% of Antarctica is covered in ice, with thicknesses exceeding 4 kilometers in some areas, making it a natural laboratory for studying climate change. Rising temperatures and global warming are causing the ice cover to gradually melt, opening up previously inaccessible regions. For example, in 2020, scientists from the University of London found that the melting of ice is uncovering new land areas and releasing methane, which could exacerbate climate changes. Ice shields such as the Ross and Weddell shields serve as important indicators of climate change and are monitored using satellite technology. These shields hold vast amounts of fresh water. Estimates suggest that if all the ice in Antarctica were to melt, global sea levels would rise by more than 60 meters. Beneath the ice cover, there is not only an extraordinary and diverse landscape, but also potential dangers for the entire human race, as changes in this region could affect climate conditions worldwide. The perception of Antarctica as a simple, icy wasteland changes dramatically when we begin to understand that beneath its dark surface lie secrets that could transform our understanding of nature and the planet's ecosystems. Scientists continue to explore these mysterious territories, and each discovery brings us closer to understanding how this hidden world influences our lives and the future of Earth. In 2020, satellite images showed that in some regions of Antarctica, the ice cover is starting to crack, indicating that the process of climate change is already underway, and we must closely monitor this phenomenon. Beneath the thick layer of Antarctic ice lie worlds of which we can only conjecture. In the year 2001, a group of Russian scientists led by Dr. Valery Lomov began studying Lake Vostok, one of the largest subglacial lakes on the planet. This lake, with an area comparable to Lake Ontario, spans 3,000 square kilometers and has a depth exceeding 900 meters. Scientists used radar surveys to detect this body of water, allowing them to determine its size and structure even under the ice cover, which reaches up to 4 kilometers in some places. Radar signals were able to penetrate the ice and reflect off the water surface, confirming the existence of such vast water bodies. The uniqueness of Lake Vostok lies in the fact that its waters remain liquid due to geothermal heat from the Earth's interior and the pressure of the ice cover above. This process has maintained the lake's ecosystem in isolation for over 1 million years, making it a unique object of study. Research indicates that these waters may harbor organisms unknown to science, and each new discovery could fundamentally alter our understanding of life in extreme conditions. For instance, in 2012, microorganisms were found that could survive in a completely closed ecosystem. These ancient water worlds, isolated from the external environment, hold secrets that could shed light on the evolution of life on Earth and even on other planets. Such isolation makes Lake Vostok not only an object of ecology, but also a significant field for astrobiological research. Scientists believe that studying such closed ecosystems could help answer the question of the possibility of life on other planets, such as Europa, a moon of Jupiter, where subglacial oceans may also exist. The water in Antarctic lakes like Vostok not only preserves ancient forms of life, but also serves as a record of time, encapsulated under the ice cover. Each new project to study these subglacial bodies of water opens new horizons for scientific understanding, and perhaps it is here that we will find answers to the most important questions about life on Earth and beyond. Lake Vostok, like other similar bodies of water, serves as a living testament to the fact that even in the harshest conditions of nature, life can emerge. Antarctica, this gloomy and mysterious continent, astonishingly hides within itself approximately 70% of all the fresh water on the planet, enclosed in a majestic ice cover. The volume of this ice is so immense that if it were to melt, the level of the world ocean would rise by as much as 58 to 40 years ago. This would be equivalent to all coastal cities worldwide being submerged, leaving only the tops of skyscrapers peeking out of the ocean waves. The water enclosed in this ancient ice is crystal clear and transparent, unlike any other on Earth. It is free from pollution, and each drop is a reflection of millions of years of history, preserved in the ice layers. When sunlight is refracted in these massive ice sheets, it creates breathtaking shades of blue and turquoise, which are simply mesmerizing. This phenomenon is known as the ice spectrum, and it can only be observed in places like Antarctica, where ice takes on forms that seem almost magical. Additionally, the temperature on the surface of the ice sheets fluctuates from -30 to -40 degrees Celsius, while beneath the ice lies a world where microbial life may exist in isolation, unaware of light and warmth. Scientists like Dr. Jonathan Steffen, who study Antarctic lakes, are convinced that the study of these waters can reveal the secrets of how life can develop in extreme conditions, similar to those that may exist on other planets. The water in these lakes possesses unique properties, and its purity allows researchers to study ancient ecosystems preserved in ice layers. Each ice core extracted from the depths provides invaluable data on climate changes that have occurred on Earth over millions of years. Changes in the content of gases and minerals in these cores can tell us about temperature fluctuations and atmospheric conditions in the distant past, and perhaps help us understand what awaits us in the future. As a result, Antarctica is not only a repository of water, but also a crucial indicator of global climate changes that can affect the lives of each of us. The height of some ice caps reaches 32 meters, and their thicknesses can exceed 3 kilometers, making this continent one of the most fascinating objects for study and observation on our planet. Imagine a world where coastal cities are gradually disappearing underwater, and new shores are forming before our very eyes. If the melting of Antarctic ice continues as predicted by climatologists, the world maps will change beyond recognition. The Netherlands, famous for their picturesque canals and polders, may become just a page in history books when the sea level rises by 1 meter, which is quite possible by the end of the 21st century. In this scenario, more than 3 million residents of this country will be on the brink of extinction, and their familiar way of life will be lost forever. Bangladesh, where the population density reaches more than 1,000 people per square kilometre, may face catastrophic consequences if the sea level rises by just half a metre. The disappearance of vast agricultural lands and the increase in the frequency of floods will create millions of climate refugees. Venice, a city that has existed for more than 1,000 years, will be threatened with complete flooding if the sea level rises by 2 meters, which could happen by the 22nd century. Streets once filled with tourists will be underwater, and the famous gondolas will remind us of the former glory of this unique place. St. Petersburg, founded by Peter the Great, will also not escape the fate of drowning if the sea level exceeds 2 meters, meaning that countless architectural masterpieces, such as the Hermitage and the Church of the Savior on Spilled Blood, will be at risk of destruction. In New Orleans, which already suffers from frequent floods, a rise in ocean level by 1 meter could make the city uninhabitable. The roar of retreating water will be heard along the new shores where houses and streets once stood. And this sound will remind us that humanity is losing what it has created over centuries. The salty smell of ocean water will begin to penetrate deep into the continents, altering familiar ecosystems and threatening the existence of many species. These changes will not happen instantaneously. They will span centuries, creating new climatic realities and uncertainties. The reverse effects of this natural process will be deeper than we can imagine, affecting not only geography, but also the social structure of societies. More than half of the world's population today lives in coastal areas, and such changes will put the lives of millions of people at risk. According to the United Nations Environment Programme, if the sea level rises by 3 meters, this will result in the inundation of 31 1 million square kilometers of land. Antarctic ice is not just frozen water, it is a genuine time capsule, preserving the atmosphere of past epochs. Under the pressure of its own weight, snow falling on the continent's surface gradually compacts and transforms first into firn and then into ice. This process can take thousands of years. For instance, in some places in Antarctica, such as the West Antarctic ice sheet, the ice thickness exceeds 3 kilometers. Within this ice, there are air bubbles that serve as tiny capsules containing atmospheric gases like carbon dioxide and methane from periods when these gases were present in the atmosphere at different concentrations. These bubbles can be dated and provide scientists with data on climate over hundreds of thousands of years. For example, research conducted in the early 2000s on an ice core taken at the Vostok station showed that climate changes on Earth over the past 450,000 years largely coincide with fluctuations in atmospheric carbon dioxide levels. Ice samples also contain particles of dust, volcanic ash, and other materials that traveled through the air in ancient times. These particles can reveal information about volcanic activity and dust storms in various regions of the planet, as well as changes in vegetation. Studies of ice cores indicate that during global warming, the level of dust in the ice significantly increases, suggesting climate change. For instance, in one such study conducted in 2009, scientists found that the level of dust in the ice over the past 100,000 years increased by 60% during periods of warming. These data help us understand how climate changes affect ecosystems and what consequences humanity might face in the future. Interestingly, ice sheets also contain isotopic traces that can indicate the origin of the water, allowing us to reconstruct the picture of ancient oceans and continents. For example, in studies focused on the analysis of oxygen isotopes, scientists conclude that at certain historical moments, sea levels were significantly higher than they are now, indicating global climate changes. These studies not only help reconstruct past climate conditions, but also predict future changes. Approximately 34 million years ago, when Antarctica began to separate from Gondwana and move towards the South Pole, the continent experienced abrupt climate changes that gradually transformed its landscape. During this period, known as the Eocene, Antarctica was covered with lush forests, where coniferous and deciduous trees grew. Surrounded by a warm ocean, it was home to diverse species of animals, including the ancestors of modern mammals and birds. However, by the end of the Eocene, around 33 million years ago, a global cooling period began, causing temperatures on the continent to gradually decrease. This climate change acted as a catalyst for the formation of the first ice sheet. Initially, glaciers began to appear in mountains such as the Transantarctic Mountains and gradually descended into valleys, covering an ever-increasing area. By the beginning of the Oligocene, around 32 million years ago, a significant portion of the continent was already covered in ice. Ice sheets, initially thin and localized, grew thicker and more extensive, forming a continuous ice cover that reached several kilometers in thickness by the middle of the Oligocene. At this time, the landscape of Antarctica underwent a dramatic change. Dense forests gave way to tundra, and then to an ice desert where temperatures rarely rose above 0 degrees Celsius. These slow but inexorable changes occurred over millions of years, shaping the climate and ecosystems we observe today. The ice sheets formed as a result of these processes continue to influence sea levels and the planet's climate system. Existing glaciers, such as the Ross Ice Shelf, extend for hundreds of kilometers and are part of a vast ice cover that occupies nearly 90% of the continent's surface. The ice shield of Antarctica is a colossal formation divided into two main segments, the eastern and western ice shields. The eastern ice shield, which is twice as large as the western, contains approximately 70% of the entire ice mass of the continent. It has an average thickness of around 3 kilometers and in some places reaches 4 kilometers. The western ice shield is significantly thinner and less stable, with its average thickness ranging from 800 meters to 2 kilometers. These two segments of the ice shield interact through glacier flows that slowly move from the center of the continent to the coast, forming ice shelves such as the Taylor Glacier and the Ross Glacier, which extend into the ocean, creating impressive ice platforms. Glacier flows move at a speed of several centimeters to several meters per year, which may seem insignificant, but over decades, this can lead to significant changes in the structure of the entire ice cover. The sound of moving ice resembles deep thunderclaps and the crackling of old wood as massive ice masses move down slopes. These sounds create an atmosphere of majestic silence, occasionally interrupted by the rustling and creaking as ice shifts, breaks, and forms cracks. From a bird's eye view, glacier flows appear as slow rivers cutting through the snow-white plateau, their jagged lines contrasting with the smooth areas where ice is relatively at rest. The topography of the ice shield affects its dynamics. Some areas experience significant movement, while in others, ice remains in place for decades or even centuries. Ice shelves like the Larsen Glacier can collapse into the ocean, triggering tsunamis that can have catastrophic consequences for coastal regions. These glaciers also play a crucial role in the global system, as their destruction can lead to sea level rise, threatening many low-lying regions worldwide. The ice shield of Antarctica is not only a reservoir of fresh water, but also a vital component of the planet's climate system, reflecting solar radiation and influencing ocean currents. Antarctica is not just an icy continent. It is a key player in Earth's global climate system. The cold air that forms over its surface creates powerful circulation currents in the atmosphere, which spread to the southern hemisphere and influence the climate in distant regions such as South America and South Africa. These currents lead to the formation of strong storms and prolonged rains, which are part of a complex mechanism where changes in one place can have significant consequences elsewhere. The cold bottom waters that form around Antarctica have immense importance. They are drawn into the depths of the world ocean, forming what is known as the global conveyor belt system, or thermohaline circulation. This process begins when cold, salty waters sink, creating density that forces them to move towards the equator, where they warm up and rise to the surface. Thus, the temperature and salinity of ocean waters in equatorial regions are the result of processes occurring at the other end of the planet. In this context, it is worth noting that around 30% of the carbon dioxide absorbed by the ocean occurs due to this dynamics, which directly affects the ocean's acidity. Research conducted by the National Oceanic and Atmospheric Administration, NOAA, in the United States shows that changes in water temperature can disrupt this balance, leading to serious consequences for marine ecosystems and ultimately for all of humanity. When glaciers, such as the Thwaites Glacier, begin to melt, they not only raise sea levels, but also affect the composition of waters, which can lead to changes in the habits of ocean inhabitants such as krill and fish, which depend on specific conditions for their survival. This interaction between the atmosphere, ocean, and ice cover demonstrates how all systems on the planet are interconnected, and how even small changes in one component can trigger a chain reaction worldwide. Antarctica is particularly important in this context, as it is the main source of cold waters that then influence marine currents, including the Gulf Stream. As a result, changes in Antarctica can lead to significant changes in the climate of Europe and North America, demonstrating how fragile this global system is. In the 21st century, scientists such as Dr. John Mercer predicted that if the pace of global warming continues, sea levels could rise by more than 1 meter by the end of the century, which would significantly impact coastal areas, including major cities such as New York and Tokyo. Amazingly, the transformation of fluffy snowflakes into a solid ice block in Antarctica is a complex and lengthy process that requires time and specific conditions. When snowflakes fall onto the surface, they initially possess a unique lace-like structure, formed by the crystalline properties of water vapor in the atmosphere. Gradually, they lose their lightness and airiness under the weight of new snow layers that continue to settle on top. This compaction process leads to the formation of granular firn, an intermediate stage between snow and ice. At this stage, significant changes occur in the material structure. Density increases, and the color changes from bright white to a more grayish hue. Over decades, sometimes centuries, firn continues to compact, transforming into crystalline ice, which bears no resemblance to the original fluffy snowflake. During this process, the density of ice increases significantly, reaching values up to 900 kilograms per cubic meter, while snow can weigh only around 130 kilograms per cubic meter. At this stage, ice becomes not only denser, but also changes its optical properties. It acquires a characteristic bluish tint, which is due to the absorption and reflection of light in the crystals. Transparency also increases significantly, allowing ice to pass light and creating stunning visual effects in ice caves and underwater rivers. Research shows that the complete transformation of snow into ice can take between 50 and 300 years, depending on climatic conditions and the thickness of the snow cover. This process of accumulation and transformation of snow into ice is crucial for studying climate changes, as ice layers preserve data on atmospheric composition over decades, sometimes even centuries. For example, the analysis of ice cores from Antarctica has allowed scientists to reconstruct the climatic conditions that existed more than 80,000 years ago, providing valuable information about the cycles of climate change and its impact on Earth. Physical processes occurring within the depths of ice sheets are governed by strict laws of nature and are difficult to observe with the naked eye. The pressure at great depths can reach enormous values due to the weight of layers of ice that can be up to 3 or 4 kilometers thick. This pressure forces air out of the crystal lattice of the ice, significantly altering its structure. At a depth of about 2 kilometers, ice begins to take on a different crystalline form, known as hexagonal. While on the surface, ice forms a cubic structure. At great depths, with increasing pressure, it becomes denser and harder due to the reorganization of water molecules. This transformation occurs gradually and can take thousands of years, creating unique conditions for the formation of ice layers. The structure of ice is not uniform. It has different densities at different depths, from less dense on the surface to more dense at the bottom, making it not just a cold mass, but a complex geological structure capable of storing information about climate over millions of years. Additionally, the temperature at the base of the ice sheet can rise to 0 degrees Celsius and even higher due to pressure and geothermal heat, sometimes leading to the formation of subglacial lakes. These lakes, such as Lake Vostok in Antarctica, located under 4 kilometers of ice, represent unique ecosystems that have existed in isolation from the rest of the world for millions of years. Research shows that such lakes may harbor microorganisms adapted to extreme conditions, making them objects of study for scientists seeking to understand the possibilities of life in harsh conditions. These invisible processes occurring in ice sheets reveal the secrets hidden deep within the Earth and can help predict how the planet's climate will change in the future. Scientists are actively conducting research, and in the 21st century, access to ice samples from great depths was obtained, allowing the study of climate changes over the past 800,000 years. For example, analysis of ice cores using radiocarbon dating can restore the concentration of carbon dioxide in the atmosphere at different times, allowing us to see how human activity affects the climate. Imagine a thick layer of ice covering Antarctica, concealing ancient landscapes that could tell us about the planet's past. The ice sheet, spanning over 13 million square kilometers, preserves mountains, valleys, and lakes that existed millions of years ago, when the climate was significantly warmer. For instance, in 2015, an international team of scientists discovered a valley that, according to geological data, could have existed during the Eocene period around 40 million years ago. Research shows that some parts of this landscape have remained unchanged since the onset of glaciation, approximately 35 million years ago. Scientists use radar imaging and geophysical studies to visualize these hidden topographical features. Beneath the ice, not only mountain ranges but entire lakes like Lake Vostok, which, according to recent data, has maintained its ecosystem in a state of hibernation for nearly 4 million years, are hidden. These ancient topographical features, invisible to the human eye, frozen in time, offer unique opportunities for studying climate changes and ecosystems that existed before glaciation. For example, analysis of samples from Lake Vostok showed that microorganisms once inhabited its waters, which could shed light on the evolution of life in isolation. Research indicates that ancient landscapes in Antarctica were home to various ecosystems, including forests and wetlands, which today seem far removed from the reality of this continent. Scientists are actively studying these landscapes to reconstruct the picture of what Antarctica looked like in epochs when it was warmer and inhabited by diverse flora and fauna. In 2000, a group of Australian geologists working in the region of the Antarctic Peninsula discovered traces of an ancient forest, estimated to be over 100 million years old, which supports the theory that Antarctica was part of the green continent Gondwana. These studies not only help us understand how Antarctica looked before glaciation, but also provide insights into future climate changes and their impact on ecosystems. Ice cores extracted from deep within show that the level of carbon dioxide in the atmosphere was significantly higher than it is today, allowing us to speculate about how the climate might change in the future. Each new layer of ice studied by scientists opens new horizons for understanding ancient ecosystems and climate conditions that could have existed on the planet. This journey into the past, occurring beneath the ice, allows us not only to see, but also to understand how life on Earth has changed over time. It's hard to imagine, but millions of years ago, Antarctica was completely different. This continent was once part of the supercontinent Gondwana, which connected modern-day South America, Africa, India, and Australia. Around 100 million years ago, during the Cretaceous period, Antarctica was covered in lush coniferous and deciduous forests. These forests covered almost the entire continent, creating a unique ecosystem where dinosaurs, the ancestors of modern mammals, and numerous other species thrived. For example, scientists have found fossils of ancient conifers like Araucaria that grew in a warm and humid climate. Tropical rainfalls filled rivers and lakes, creating rich ecosystems teeming with life. At that time, the continent was home to animals such as dinosaurs, including the giant lizard Maniraptor, which could reach lengths of over 7 meters. Gradually, starting from the Jurassic period, the movement of continents led to the isolation of Antarctica. Around 70 million years ago, it began to drift towards the South Pole. This process was not instantaneous. It took tens of millions of years, and as a result, Antarctica lost its connection with other continents. With each passing million years, the climate became increasingly harsh. The abundance of sunlight that once warmed the forests began to cool the land, leading to the formation of glaciers that eventually covered the entire continent. The ice sheet we observe today is the result of this long process. Scientists suggest that during the maximum glaciation period, which occurred approximately 2 million years ago, the ice thickness in some places reached more than 3 kilometers. This led to the disappearance of ecosystems that once flourished, making it impossible for life to exist. Antarctica, once teeming with life, became a lifeless ice desert. The existence of forests and the diversity of animal life became a part of the distant past, leaving only fossils to remind us of how vibrant life once was on this now harsh continent. Scientists continue to find evidence in fossils that the climate in Antarctica was significantly warmer, and even in some places, plants similar to modern eucalyptus grew. Have you ever wondered what it was like in Antarctica when it was covered in green forests and inhabited by exotic animals? Fossils found in this harsh land tell incredible stories about how life once thrived here. For instance, in the Transantarctic Mountains, fossils of dinosaurs like Hypsilophodonts, which could reach lengths of up to 10 meters, have been discovered. These herbivorous dinosaurs had long, flexible necks and feathered bodies, suggesting they made sounds similar to low humming as they moved through the forests. Around them grew ancient ferns and glossopterids, plants that could reach the size of small trees. These heat-loving plants with wide leaves created dense shade and filled the air with a sweet scent, reminiscent of the tropics. In 1991, a group of Australian paleontologists led by Professor Peter Copps discovered fossils of glossopteris trees in a region now covered by lifeless ice fields. These trees, reaching heights of up to 30 meters, had bark that could be bright green, and their seeds resembled modern nuts. While Antarctica is now silent and cold, it once teemed with life, filled with the rustling of leaves and the chirping of birds, which were likely impressive in size and variety. Additionally, fossils of marine creatures like ammonites and marine reptiles confirm the presence of warm seas around the continent. These marine inhabitants could reach lengths of up to 5 meters, and their vibrant colors might have reflected sunlight filtering through transparent waters. Scientists have also found remains of early mammals that could roam the green shores, inhaling the rich aroma of marine algae and blooming plants. Each of these fossils holds a story about the warm climate that once prevailed in this region. Antarctica, once a center of biodiversity, is now a cold and silent landscape. Every discovered fossil fragment is a piece of the puzzle that helps reconstruct the picture of life that existed in Antarctica millions of years ago. Fossils of glossopterids found at Cape Adams show that these plants could grow in conditions that now seem impossible for life. Paleobotanists such as Dr. Catherine Martin study these findings to understand how climate conditions changed and what factors led to the disappearance of this ecosystem. Understanding these processes helps us better comprehend how climate changes affect modern ecosystems. Antarctica, once covered in green forests and picturesque ecosystems, began to face inevitable changes approximately 34 million years ago. At that time, the continent started to form its first glaciers, gradually covering its mountain ranges. Paleoclimatologists such as Dr. Emily Brown from the Institute of Geological Research point out that it was during this period that the planet's temperature began to drop, leading to a sharp change in climate. The forests that once thrived on the territory of Antarctica began to retreat, giving way to harsh conditions that could not support the usual flora and fauna. Gradually, the soil froze, and trees like Glossopteris began to die out, leaving behind patches of bare ground covered in ice and snow. This was the time when animals, such as the primitive ancestors of modern penguins and marine mammals, began to migrate in search of warmer places. Research has shown that many species were unable to adapt to the rapidly changing conditions and became extinct. Over millions of years, this process continued, and by 14 million years ago, the temperature had dropped to such a level that glaciers finally covered the entire continent, transforming it into an icy desert. This ice cover became one of the largest ecosystems in the world, but in a different, more severe form. Glaciers reaching thicknesses of several kilometers formed ice shields that still preserve the secrets of the past, with fossilized remains and traces of ancient life lying beneath them. Each spring, as the ice begins to melt, geologists and paleontologists like Dr. James Taylor study these areas, trying to unravel the mysteries left behind by nature. Plate tectonics and ocean currents played a pivotal role in shaping the climate of Antarctica, transforming it into the icy continent we know today. The separation of Antarctica from Australia and South America, which began around 100 million years ago, was a turning point in the region's climatic history. This process created the circumpolar current, which, acting as a powerful cold barrier, encircled the continent, isolating it from warm equatorial waters. As a result, temperatures in Antarctica began to gradually decrease, and the continent became covered in ice sheets. Over millions of years, this cold oceanic flow impeded heat exchange, contributing to the formation of a unique ecosystem where ice and snow became the dominant landscape features. The circumpolar current, with a length of around 12,000 kilometers, also serves as a significant temperature regulator in the oceans, influencing climate conditions not only in Antarctica, but around the world. This current, in turn, altered the directions of other ocean currents, leading to changes in climatic patterns in distant regions such as North America and Europe. For instance, changes in ocean water temperature caused by circulation could affect phenomena like El Niño, altering rainfall and temperatures in the tropics. Research results indicate that such global climatic changes began to form precisely during the period when Antarctica separated from other continents. As a result of these processes, Antarctica became one of the coldest places on the planet, where the average winter temperature drops to -50 degrees Celsius, and in the summer months it rises only to -30. At the same time, ice sheets reaching thicknesses of 3 kilometers play a critical role in global sea levels, as the melting of glaciers could lead to a rise in ocean levels by several meters, threatening coastal regions worldwide. Changes in ocean currents and climate, initiated millions of years ago, continue to influence our planet, underscoring the interconnectedness of all climatic systems and their fragility. In the beginning of the 18th century, when Europeans were just beginning to explore the southern latitudes, Antarctica remained a mystery, shrouded in ice and myths. James Cook, an English navigator and explorer, crossed the southern polar circle during his second circumnavigation in 1773. But he was unable to see the continent itself. Although he meticulously charted the coasts of New Zealand and the Pacific Ocean, his attempts to discover the southern lands were unsuccessful. Nevertheless, Cook made an important discovery, noting that on the south lay vast waters filled with icebergs and harsh conditions that posed insurmountable barriers for researchers. Several decades later, in 1820, a Russian expedition led by Fadej Bellingshausen and Mikhail Lazarev on the ships Vostok and Mirny was the first to sight the shores of Antarctica. Their ships, breaking through ice fields, creaked, and the icy wind burned the faces of the sailors, creating a sense of encountering something otherworldly. Bellingshausen, who was among the first to notice the continent, described the gleam of ice on the horizon as if it were covered with millions of diamonds reflecting sunlight. The moment of discovery became the culmination of a long and dangerous journey. The sailors were filled with a sense of discovery when their ships finally approached the massive ice cliffs rising from the ocean. These ice formations, reaching heights of up to 100 meters, stood like ancient fortresses guarding their secrets. The attack of the cold wind made them tremble, but adrenaline and the thirst for knowledge drowned out the fear of the unknown. With each minute spent in these waters, the sailors bore witness to the grandeur of nature, creating maps and recording observations that became the foundation for scientific research decades later. Observing the ever-changing forms of ice, they realized that this was not just a lifeless space, but an ecosystem teeming with life, where penguins and seals reigned. These discoveries opened a new chapter in the history of geographical research, paving the way for future expeditions that continued to explore this harsh continent in search of its mysteries and resources. 80 years later, in 1883, the American Antarctic expedition led by John Wilkes was already actively researching the coasts of Antarctica, making even more detailed maps and expanding the known lands. In the age when intrepid explorers challenged the unyielding expanses of Antarctica, three names stand out particularly brightly: Ernest Shackleton, Robert Scott, and Roald Amundsen. These men became symbols of heroism and human endurance, demonstrating extraordinary courage in the face of unimaginable hardships. In 1910, Amundsen, a Norwegian polar explorer, planned his expedition to the South Pole, aiming to outdo his competitors and become the first to reach this inaccessible summit. Simultaneously, Scott, a British officer, led his own expedition, believing his team could outpace Amundsen. Both expeditions set off in 1911, and the rivalry between them became a true struggle for survival and glory. In January 1912, Amundsen and his team reached the pole, leaving behind a message: "We have arrived first." Scott, who arrived at the pole only a month later, encountered a horrifying tragedy. His team was trapped in the ice, exhausted and lacking essential resources. As a result, in early March 1912, all 5 members of his team perished, leaving behind journals filled with anguish and suffering. While Scott was battling for survival, Shackleton, who led the expedition on the ship Endurance in 1915, faced an even more terrible fate when his vessel became trapped in the Weddell Sea ice. The team of 28 people survived thanks to their incredible resilience. They endured months in the icy wilderness, fighting against temperatures of -50 degrees Celsius and constant hunger. Their physical ordeals were horrendous. The cold seeped into their bones, and the blinding whiteness of the snow made each step a trial. Shackleton, demonstrating leadership, never lost hope and organized rescue operations that allowed all his people to survive. Ultimately, in August 1916, they reached the shores of South Georgia, where they could obtain help. These expeditions became not only a history of reaching the pole, but also a testament to human endurance in the face of harsh conditions that make us ponder what humans are capable of in the pursuit of knowledge and glory. Scott left behind journals detailing his struggles and battles, while Shackleton became a symbol of courage, proving that even in the most desperate situations, there is a chance for survival. In the thousands of miles of icy continent, where only cold and solitude reigned, the spirit of these explorers continues to inspire new generations. Modern scientific expeditions to Antarctica are opening a new chapter in the study of this icy continent, where science encounters harsh conditions that require advanced technologies. Since the beginning of the 2000s, scientists from various countries, such as the USA, Russia, and Germany, have been actively using cutting-edge tools to study subglacial lakes and climate. For instance, in 2018, an international team led by Dr. Emily Hayes from the University of Auckland, using ice drills, was able to drill through ice to a depth of over 3 kilometers to access Lake Vostok, one of the world's largest subglacial lakes. These drilling rigs, resembling giant mechanical probes, can penetrate thick layers of ice, producing dull sounds reminiscent of a working engine, and are used to extract samples of water and sediments that have been isolated from the outside world for millions of years. Additionally, scientists are developing robotic devices such as underwater drones that can navigate beneath the ice cover, exploring subglacial ecosystems. These robots, equipped with cameras and sensors, can transmit data in real time, allowing researchers to control their operations remotely. At Antarctic stations such as the Mirny station on the coast of eastern Antarctica, scientists live in constant cold, where temperatures can drop below -30 degrees Celsius. Here they work on international projects such as the long-term climate observation of Antarctica and use technologies like satellite systems to monitor changes in the ice cover. The scientific results of these studies help us better understand climate change and its impact on sea levels. For example, in 2019, researchers found that the rate of melting of the Tweddell Glacier had increased by 8% over the past 30 years. Which could lead to a rise in sea levels of 3 meters by the end of the century if this process is not stopped. Modern technologies not only facilitate the work of scientists, but also open new horizons in understanding the mechanisms that govern our planet. While outside the Antarctic stations, blizzards rage and temperatures drop to levels where life seems impossible, advanced technologies become a reliable support for humanity in its quest to unravel the mysteries of this frozen world. Modern research shows that beneath the ice cover, there are not only frozen waters, but also unique ecosystems capable of existing without sunlight, challenging our understanding of life on Earth. Few people consider how scientists uncover the mysteries hidden beneath kilometers of ice. To do this, they employ modern methods such as radar and seismic surveys, which enable them to peer into the depths of Antarctica. Radar systems operate by transmitting radio waves that penetrate the ice and reflect off the boundary between the ice and the subglacial surface. These systems can send waves with frequencies ranging from tens of megahertz to several gigahertz, allowing for the acquisition of high-quality images of hidden landscapes. The resulting data are in the form of radargrams, graphs that clearly depict the profile of the subglacial terrain, including the characteristics of the ocean floor and subglacial lakes. For instance, in 2000, an American research team led by Dr. Edward King used radar methods to study the subglacial Lake Vostok, located more than 4 kilometers beneath the ice. With the help of radio waves, they discovered that the subglacial lake is not just a body of water, but an ecosystem containing microorganisms that exist in complete isolation from the outside world. Seismic methods add another dimension to the study of subglacial landscapes. Researchers create artificial sound waves that penetrate the ice and reflect off various layers, allowing them to create a three-dimensional image of the terrain. Sound waves generated using explosives or specialized seismic sources are detected by arrays of sensors placed on the ice surface. This provides information about the structure and dynamics of the subglacial landscape, including the thickness of the ice and the nature of the geological formations. For example, in 2001, as part of the Seismic Investigation of Antarctica project, scientists were able to determine the presence of a subglacial canyon with a depth exceeding 3 kilometers. These methods not only aid in the study of the region's geology, but also contribute to an understanding of climate changes, as subglacial waters can influence the level of the world's oceans. Scientific developments in this field are continually advancing, leading to increasingly accurate data on what lies beneath the ice. Subglacial landscapes in Antarctica significantly influence the dynamics of glaciers and, consequently, global climate. The complex structure of the subglacial terrain determines the speed and direction of glacier movement. For instance, glaciers flowing through valleys tend to accelerate due to the valley's shape, which facilitates faster ice movement down the slope. Conversely, mountain formations can create obstacles, slowing down glacier movement and altering their path. Scientists from the University of Wisconsin and the Institute of Polar Research conducted a study in 2009, revealing that subglacial lakes, such as Lake Vostok, play a crucial role in this process. These lakes, located under a multi-kilogram ice shield, can be filled with meltwater resulting from geothermal heating. This meltwater can act as a lubricant, accelerating ice movement and allowing it to slide more easily over the subglacial surface. Specifically, in 2012, scientists found that when Lake Vostok was filled with water, the glacier covering it began to move significantly faster than before. Therefore, the presence of subglacial lakes and meltwater areas affects the speed and direction of glacier movement, which in turn impacts sea level and climate. A complex network of subglacial channels and water bodies forms a dynamic system where changes in one element can trigger a chain reaction in others. A study conducted in 2014 by a group of scientists from the National Oceanic and Atmospheric Administration in the United States showed that changes in subglacial landscapes can lead to accelerated glacier melting, which could raise sea levels by several meters over the next 100 years. Understanding these interconnections is critically important for predicting future changes in the ice sheet and assessing their impact on global climate. Modern technologies, such as radar sounding and satellite observations, enable researchers to obtain data on subglacial terrain with an accuracy of several meters, providing a better understanding of how the invisible subglacial world influences surface processes. For example, in 2016, scientists made a significant discovery, showing that some glaciers in West Antarctica are losing volume faster than expected due to the formation of subglacial channels that facilitate faster movement. These findings underscore the need for further research and monitoring of subglacial processes to adequately assess the risks associated with climate change. Imagine an ice river that doesn't flow, but rather slowly crawls, like an enormous, relentless monster. In Antarctica, colossal glacial streams, such as Taylor Glacier and Weddell Glacier, move from the continent's center to the coast at speeds sometimes reaching several meters per day. These streams consist of multi-kilometer thick ice that has accumulated over thousands of years. Shelf glaciers like Ross Glacier float on the ocean's surface, forming vast platforms that support immense volumes of ice. When underwater currents and temperature changes affect their base, catastrophic events occur. The calving of icebergs the size of small countries, such as Iceberg 68, which broke off from the Larsen Shelf in 2017, causes a thunderous roar, similar to a peal of thunder, and generates waves that can shake boats nearby. These sounds, ranging from a soft crackling to a powerful rumble, create a unique symphony of the ice world that is constantly in motion and change. On the surface of an active glacier, one can feel a vibration as the ice shifts and breaks under its own weight, giving the sensation that the Earth itself is breathing. Glaciers like Fernando Nobre Glacier can be up to 3 kilometers thick, and their movement not only affects sea levels but also global climate conditions. When glaciers retreat, they release enormous volumes of fresh water, which in turn can cause changes in ocean currents and ecosystems. 80% of the fresh water on the planet is in Antarctic ice, and if it all melted, sea levels could rise by more than 60 meters. The processes occurring in this frozen realm have global consequences and require deep understanding to predict how they will impact the future of our planet. In the depths of Antarctica, there are processes that may seem contradictory. Beneath the ice cover, where temperatures often drop below -30 degrees Celsius, there is a powerful geothermal heat. This heat, emanating from the Earth's interior, warms the lower layers of the ice sheet, sometimes leading to melting at the base. Volcanic activity, manifesting as underwater volcanoes and hot springs, plays a significant role here. For example, active volcanic complexes have been discovered under the ice cover of Antarctica, such as Mount Vinson, which reaches a height of 14,837 meters, and others in the area of Cygne Island, which can release heat that contributes to melting. This melting, in turn, creates water that accumulates under the ice, acting as a lubricant and facilitating its movement over the underlying surface. Research shows that the presence of water under the ice significantly accelerates its sliding speed. For example, in 2015, a group of scientists led by Dr. John Elswick from the University of St. Andrews discovered that the Totten Glacier, the largest in eastern Antarctica, was moving faster than previously thought, precisely due to this process. The temperature contrast between the surface and the interior is striking. The ice cover on the surface can reach -40 degrees, while just a few dozen meters below, the temperature can rise to 0 or even higher, thanks to geothermal heating. This contrast between the icy cold on top and the hidden heat below creates unique conditions for the dynamics of glaciers. Observations show that under the influence of geothermal heat, even the most massive glaciers, such as the Larsen Glacier, can spread, altering sea levels and ocean levels. There are also hot springs, such as those on Deception Island, which rise up and can create conditions for melting around them. These sources not only heat the ice, but also nourish ecosystems, allowing life to exist in extreme conditions. Thus, geothermal heat in combination with the pressure of the ice mass creates a complex system that affects the movement of glaciers and sea levels. In the dark, cold depths of the Antarctic waters, there hides a remarkable world that most people are not even aware of. Here, unique creatures thrive in conditions that would be fatal for most organisms. One of the most astonishing inhabitants of the ocean floor is the giant sea spider, which can reach a diameter of up to 30 centimeters. These spiders have 8 long legs covered in bristles, allowing them to move across slippery rocks and underwater cliffs. Their bodies are transparent, and in the dark, they glow like ghosts, creating an atmosphere of mystery. Adaptation to extreme conditions includes the presence of a special antifreeze in their blood, which prevents freezing. This allows fish like the Antarctic lamprey to survive in cold water, with temperatures dropping to -2 degrees Celsius. These fish have long, slender bodies covered in slime and can remain motionless for extended periods, waiting for suitable prey. Their eyes, like black abysses, gleam in the light of researchers' lamps, creating a frightening sight. Invertebrates such as sea stars and sea urchins also manage to survive in these harsh conditions. These creatures slowly move across the bottom, using their appendages to search for food like algae and small organisms. Their bright colors contrast with the dark waters, and some species even use bioluminescence for communication or to attract prey. An important element of the ecosystem are the underwater currents that bring nutrients essential for life. These currents create complex systems that support life on the ocean floor, despite the absence of sunlight. Each year, researchers venture into these waters to study how organisms adapt to changing conditions, such as rising sea levels and changes in water temperature. It is interesting to note that, according to data collected in 2017, more than 30 new marine species were discovered in Antarctica, indicating the richness and diversity of the underwater life that remains a mystery to science. Bioluminescence in the depths of the ocean is not just an interesting fact, but a true magic of nature, manifesting in the dark waters of Antarctica. Numerous deep-sea organisms, such as fish and invertebrates, are capable of producing their own light thanks to special organs or symbiotic bacteria living in their bodies. For example, such fish as the Antarctic bioluminescent fish possess special light organs that emit a bluish light. This light serves to attract prey, deter predators, or find mates. Research conducted in 2018 showed that many of these organisms can change the color of their luminescence, from a soft blue to a bright green or even reddish, making them even more attractive and effective in their struggle for survival. One of the unique adaptations of deep-sea creatures is their ability to maintain transparency, allowing them to blend with their surroundings and avoid predators. For instance, transparent jellyfish and some shrimp species can remain undetected in waters filled with light and shadows. Additionally, some deep-sea organisms have adapted exceptionally well to extreme conditions, facilitating survival at temperatures close to 0 degrees Celsius. In 2019, an expedition led by Dr. Emily Hart from the Seattle Oceanographic Institute discovered that some species of Antarctic fish can survive even at temperatures as low as -12 degrees. Their blood contains antifreeze proteins that prevent tissue freezing. These adaptations make Antarctic inhabitants true wonders of evolution. Deep-sea organisms not only astound with their bioluminescence, but also demonstrate remarkable mechanisms of survival in conditions that seem inhospitable to life. For example, some of them can produce light through a chemical reaction involving luciferin and luciferase. These substances interact, creating light that can have different wavelengths. As a result of this interaction, organisms can emit light of various colors, adding a touch of magic to their existence. Each such adaptation is not just a result of chance, but a carefully selected characteristic by evolution, allowing them to survive in these harsh conditions. The unique abilities of Antarctic organisms continue to amaze scientists, opening new horizons in understanding life on Earth. Research shows that even in the darkest and coldest corners of the planet, life finds ways to exist and thrive. In the extraordinary conditions of Antarctica, where temperatures can drop to -20 degrees Celsius, life not only exists, but also demonstrates incredible abilities to survive. Microorganisms living in dry valleys, such as the McMurdo Valley, have adapted to extreme conditions using unique biochemical mechanisms. For example, in salt lakes like Lake Vostok, scientists have discovered bacteria that can remain in a state of dormancy for decades without losing their viability. These microorganisms use minimal energy, allowing them to survive in conditions where resources are extremely limited. Research shows that some of them can even perform photosynthesis, even under constant ice, using light that penetrates through a thin layer of crystals. Within porous rocks like shungite, osteobacteria live, which can break down organic substances brought by meltwater and produce oxygen, thus supporting the life of other organisms in these harsh conditions. These microorganisms have demonstrated the ability to repair DNA, allowing them to recover from ultraviolet radiation, as well as to synthesize protective proteins that help them avoid the destructive effects of low temperatures. The study of such forms of life not only expands our understanding of the Earth's ecosystem, but also opens new horizons in the search for life on other planets. For example, scientists from the University of Washington, under the leadership of Professor Larry Campbell, study the abilities of Antarctic organisms to determine how such forms of life could exist on Mars or Europa, one of Jupiter's moons, where extreme conditions are also observed. These studies show that even in the most lifeless places on our planet, life finds ways to adapt and survive. For instance, as a result of an expedition in 2018, researchers discovered a new type of bacteria that can convert methane into carbon dioxide, which is crucial for understanding the carbon cycle in such conditions. The abilities of these microorganisms are astonishing and inspiring, highlighting the incredible diversity of life on Earth and its ability to adapt to the most severe conditions. Imagine ice-covered lakes that have existed in complete isolation from the outside world for millions of years, hidden beneath thick layers of ice. Lake Vostok in Antarctica, for example, is located under an ice cap more than 3 kilometers thick and is one of the largest subglacial lakes on the planet. Scientists believe that this lake has been isolated for over 40 million years, creating a unique ecosystem. In 2013, Russian researchers from the Institute of Polar and Marine Research, named after Vitus Bering, first drilled through the ice and extracted water from the lake. Special equipment was used to minimize contamination of the samples. Microorganisms were found in the water samples that had not been previously encountered by science, and their genetic material indicates evolution in conditions vastly different from those on the Earth's surface. Lake Whillans, located in western Antarctica, also represents a world where life exists beyond standard biological concepts. In 2009, a group of scientists from the University of California, Los Angeles, discovered that this lake harbors bacteria capable of surviving in extreme pressure and low temperature conditions. Researchers used sonars to take samples, and the results showed that the water had a high concentration of hydrogen sulfide, indicating unique metabolic processes. Lake Ellsworth, another subglacial lake, became the subject of study in 2006 when an international team of scientists conducted drilling. Organisms were found in the samples that are believed to have no counterparts on the surface, making the ecosystem of this water body a mystery to biologists. Research shows that these microorganisms have evolved in conditions where sunlight did not reach the water for millions of years, making them unique samples for studying adaptation processes in extreme conditions. Water in subglacial lakes has a unique chemical structure that lacks oxygen, creating conditions for anaerobic organisms. Scientists believe that in such isolated ecosystems, species may have evolved independently of the rest of the biosphere. These lakes serve as living laboratories where one can study how life can adapt to the harshest conditions. Research on subglacial lakes continues, and each new discovery opens doors to a world about which we know very little. In 2020, a team of scientists from the National Science Foundation of the USA successfully drilled into Lake Whillans and extracted samples that demonstrated the presence not only of bacteria, but also of complex microorganisms such as archaea, highlighting the diversity of life in these ecosystems. Each of these lakes is a window into an ancient, untouched world that holds secrets that could change our understanding of life on Earth. In subglacial lakes, the keys to solving questions about how life can exist in conditions we consider extreme lie hidden. For example, water from Lake Vostok contains high concentrations of methane and hydrogen sulfide, indicating the presence of unique biochemical cycles that may function differently than in standard ecosystems. In 2000, scientists from the University of California, San Diego, analyzed samples from Lake Vostok and found traces of ancient life forms that could have existed millions of years ago, opening new horizons in the study of evolutionary processes. Under-ice lakes in Antarctica are not just geographical formations, but true laboratories for astrobiologists seeking to unravel the mysteries of life on other planets. The conditions in these lakes can serve as a model for studying moons of Jupiter, such as Europa and Ganymede, and Saturn's moon Enceladus, where liquid water is also believed to exist beneath the icy crust, making them potentially habitable. For example, Lake Vostok, isolated from the outside world for millions of years, offers unique conditions for studying microbial life that survives in extreme conditions like low temperatures and high salinity. In 2012, Russian scientists drilled through the ice and discovered living organisms in this lake that had never seen light and had no access to organic matter, indicating the possibility of self-sustaining ecosystems. Studies of under-ice lakes allow scientists to develop new technologies, such as autonomous underwater vehicles, which can explore inaccessible areas without disrupting the ecosystem. These developments not only benefit the study of Antarctica, but can also be adapted for missions to other planets. For instance, in 2020, NASA announced plans to send a mission to Europa, which will use technologies developed during Earth-based research. Understanding how life can survive in isolated and extreme conditions helps scientists formulate hypotheses about the possibility of finding life on other celestial bodies. If life can survive conditions similar to those found in Antarctica's under-ice lakes, this opens the door to searching for life on moons where liquid water may be hidden beneath ice. 80% of Europa is covered in ice, and its sub-ice oceans may contain conditions similar to those found in Antarctica. Additionally, research shows that Enceladus has active geysers that eject water vapor into space, further indicating the presence of water beneath the icy crust. These discoveries underscore the importance of Antarctica as a natural laboratory where scientists can conduct experiments and test equipment that will later be used in space. In 2020, a team of researchers from the University of California, San Diego, developed a special probe that can drill through ice and analyze water samples for organic compounds, which could lead to new discoveries not only in Antarctica, but beyond its borders. Antarctic ice cores are not just frozen masses, but true archives of ancient climate on our planet. Each of these cores, which are cylindrical ice samples with a diameter of about 10 centimeters and a length of several kilometers, contains information about the climate conditions that existed on Earth over hundreds of thousands of years. Layers of ice accumulating year by year form annual rings, similar to those seen in the cross-section of a tree. Scientists like Dr. David Latimer from the National Science Foundation in the United States study and analyze these cores to understand how temperature, atmospheric composition, and even volcanic activity have changed over time. Each centimetre of this ice is a page in the history book of Earth, where one can read about the gases present in the atmosphere, how the level of carbon dioxide changed, and what natural disasters occurred. The deepest cores extracted from ice caps can contain ice up to 800,000 years old, allowing scientists to look back into the past for an entire epoch. For example, a core retrieved in 2012 in eastern Antarctica allowed researchers to study climate changes over the last 100,000 years, providing data on how sea levels changed and what changes occurred in ecosystems. Analyzing these samples, scientists can identify patterns that will help predict the future of our planet in the face of global warming. These ice archives become windows through which we can see how the Earth's climate system reacted to natural and anthropogenic changes, which is crucial in the face of the modern challenges humanity faces. Layers that appear uniform are, in fact, full of history. They have recorded moments when volcanoes erupted, when ice ages came and went, and when life on Earth faced mass extinctions. For instance, during work on cores in 2015, scientists found traces of volcanic ash from activity that occurred around 100,000 years ago, confirming the link between volcanism and climate change. Each sample collected from these cores helps not only to restore the picture of the past, but also to understand how we can adapt to the changes that are already happening. Studying these ice cores is not just the work of scientists, but a real hunt for data that can change our understanding of Earth and its climate. To study climate changes on Earth, scientists use ice cores, which serve as true archives of ancient atmosphere. Drilling ice is a complex and high-tech process requiring specialized equipment. Modern drilling rigs, such as drive and drill and core drill, can penetrate to depths of up to 3 kilometers, extracting ice cylinders with diameters of up to 10 centimeters. These cores, composed of multi-layered ice, are carefully removed and placed in special containers to prevent damage and melting. Each core is labeled and documented to preserve information about its location and depth. Transporting such samples to the laboratory requires special conditions. The ice is placed in refrigerators, maintaining a temperature not higher than -18 degrees Celsius to preserve the structure and properties of the ice. After transportation, a thorough analysis begins. Scientists first conduct a visual inspection of annual layers to assess their thickness and color, which can reveal information about climatic conditions in different historical periods. Then, more advanced methods such as mass spectrometry are applied, allowing the study of the composition of air bubbles trapped in the ice. This air, preserved in ice layers, provides insights into the composition of the atmosphere in the past. Isotopic analysis of the ice itself helps determine when these layers formed and how the climate changed. Such research requires significant time and patience, as each sample may undergo various tests and checks before the results are published. Scientific teams from different countries, including the United States, Norway, and Japan, collaborate to combine their data and create a more comprehensive picture of the climate changes that occurred on the planet over the last hundreds of thousands of years. For example, in 2012, a successful operation was conducted in Greenland to extract a core longer than 3 kilometers, which became the deepest ice core ever retrieved in that region. This core provided a unique opportunity to study the past climate and identify cycles of warming and cooling that occurred on the planet. Amazing how accurately ice cores can tell us about Earth's past climate. Scientists use the ratio of oxygen isotopes in water molecules to determine the temperatures of ancient epochs. For example, in 2000, a group of researchers from Leiden University, led by Dr. Martijn Brown, discovered that the ice core extracted from Antarctica showed a sharp change in temperature around 100,000 years ago, confirming the presence of ice ages. Each time glaciers advance or retreat, they trap air that was present at the time of ice formation. These air bubbles are true time capsules, allowing researchers to analyze the composition of ancient atmospheres. Specifically, the concentration of carbon dioxide and methane released from these bubbles helps us understand how the climate has changed over millions of years. In the 1990s, scientists from the California Institute of Polar Research found that the level of carbon dioxide in the atmosphere during ice ages did not exceed 300 parts per million, while in interglacial periods it rose to over 500 parts per million. This cyclical alternation of ice ages and interglacial periods observed in the data indicates natural climate changes that occurred on Earth. However, recent data obtained in 2020 by scientists from the University of London showed that the current increase in the concentration of greenhouse gases is happening 10 times faster than any changes in the atmosphere over the past several million years. These findings not only highlight the importance of studying climate history, but also create a sense that we can travel through time, reconstructing the climatic conditions in which our ancestors lived. Thus, ice cores become not just a research tool, but true windows into the past, allowing us to look at how the climate has changed over eons. Volcanic activity in Antarctica is one of the most unexpected aspects of this icy continent, although many are unaware of its influence on the climate. The most famous active volcano is Erebus, located on Ross Island. It is one of the most active volcanoes in the world, and according to scientists, its latest eruptions were recorded in 2007 and 2008. The constant fumarolic activity of Erebus leads to the formation of a smoke column that rises above the snow-capped peaks, creating a contrast between the black volcanic ash and the whiteness of the ice. The smell of sulfur emanating from the fumaroles fills the cold air, adding an air of mystery to this harsh place. But Erebus is not the only volcano capable of affecting climate conditions. Mount Melbourne, located on Heard Island, also exhibits its activity. In 2012, its eruption resulted in the release of a significant amount of ash into the atmosphere, which in turn affected the local ecosystem and temperature regimes. Mount Deception, located in the Antarctic archipelago of the South Shetland Islands, is known for its unique caldera lake, which periodically boils and releases steam into the atmosphere. Its activity creates areas of melting at the base of glaciers, leading to the instability of the ice cover. Research shows that such volcanic processes can cause local temperature changes, and the release of particles into the atmosphere can reflect solar radiation, which can affect the global climate. For example, eruptions in Antarctica can release volcanic aerosols that, according to research, can lower temperatures by tens of degrees in regions far from the eruption. This highlights the complexity and multifaceted nature of the climate interaction system on our planet. Volcanic activity in Antarctica not only shapes the landscape, but can also significantly influence climate conditions, both within the continent and beyond its borders. Erebus, Melbourne, and Deception continue to remind us that beneath the ice cover of Antarctica lie forces capable of changing the climate, not only locally, but also globally. The ice cover of Antarctica is not just a massive expanse of ice. It is a gigantic climatic machine that reflects the multi-generational cycles of Milankovitch. These cycles, named after the Serbian scientist Milutin Milankovic, are periodic changes in the Earth's orbit and the tilt of its axis, occurring every tens of thousands of years and affecting the amount of solar radiation reaching the planet's surface. As a result of these changes, Earth experiences significant temperature fluctuations, leading to the alternation of climatic epochs such as ice ages and interglacial periods. For example, the last ice age maximum occurred around 20,000 years ago, when most of North America and Europe were covered by thick layers of ice and the global sea level was lower. Studies of ice cores extracted from Antarctica show that the concentration of greenhouse gases like carbon dioxide and methane varied in accordance with these astronomical cycles. These cores, containing gas bubbles, allow scientists to reconstruct past climatic conditions, demonstrating how increased solar radiation due to changes in the Earth's axial tilt led to higher temperatures and increased greenhouse gas concentrations in the atmosphere. For instance, data from the cores indicate that during interglacial periods, temperatures could be several degrees higher than they are today, creating warmer conditions on the planet. Thus, the ice cover of Antarctica serves as a kind of repository of Earth's climatic history, recording temperature changes and greenhouse gas levels over millions of years. In this context, ice layers can be seen as pages of a book on the evolution of climate, where each layer is a testament to the interconnectedness of terrestrial processes and cosmic cycles. For example, over the past 300,000 years, scientists have found that the level of carbon dioxide in the atmosphere oscillated between 200 and 400 parts per million, directly linked to temperature fluctuations on the planet. These data underscore the magnitude of climatic changes driven by astronomical cycles and their potential impact on life on Earth. Ultimately, the ice cover of Antarctica is not just a frozen surface. It is an active participant in global climatic changes, recording complex interactions between solar radiation and terrestrial climatic conditions over millions of years. Modern research shows that the influence of these cycles is felt even today, as we observe climate change caused by human activity, which threatens not only ecosystems, but the future of humanity itself. Chemical analysis of ice cores from the Vostok station demonstrates that even small changes in gas concentrations can lead to significant climatic changes, calling into question the stability of current climatic conditions. The dry valleys of McMurdo in Antarctica represent a unique ice-free territory that is so unusual it resembles a landscape from another planet. These valleys, situated between the Emperor Range and ice sheets, appear as reddish-brown rocks covered with a dark desert tan. There is no snow here, and this is not coincidental. A unique combination of geographical conditions creates a distinctive microclimate. Strong katabatic winds blowing from the mountains blow away the snow, while the low humidity in the air prevents its formation. As a result, the valleys look completely alien, with a stony surface reminiscent of Martian landscapes. Inside these valleys lie the dried-up beds of ancient rivers that once flowed through this land and now only serve as a reminder of the past. Along the shores of salt lakes, one can see crystals of salt sparkling in the sun, formed due to the evaporation of water. Only rare patches of lichens, capable of surviving in such harsh conditions, break the monotony of the rocks. These organisms survive in these conditions thanks to their ability to adapt to extreme climates. It is interesting that the temperature in the valleys can vary from -20 degrees Celsius in the summer to -80 degrees in the winter. Scientific research shows that in these valleys, some of the lowest levels of precipitation on the planet have been recorded, making them unique in a geographical sense. The dry valleys of McMurdo are not only a geological wonder, but also a place for scientific research, where scientists study conditions similar to those that may exist on other planets like Mars. Such research helps to understand how life can exist in extreme conditions and what factors are necessary for its survival. The secret of the subglacial mountain ranges of Antarctica evokes both surprise and admiration. For instance, the Gamburtsev Mountains form a massive mountain system stretching over more than 300 kilometers, entirely hidden beneath kilometers of ice. The peaks of these mountains reach heights of over 2,000 meters, placing them on par with the Alps. Geological research indicates that these mountains are composed of various types of rock formations, including metamorphic and sedimentary rocks, making them unique in this snow-covered landscape. Their discovery became possible thanks to radar and seismic studies conducted in the early 2000s. Scientists working on the Sliding Under Ice project used advanced technologies, such as ice boreholes, to analyze the structure of the Earth beneath the ice sheet. They were astonished to find such a large mountain system at the center of the continent, where previously it was assumed that only a flat plain lay beneath the ice. The origin of these mountains remains a subject of debate among geologists. Some researchers believe they were formed as a result of the collision of ancient continental plates, while others propose that volcanic activity may have contributed to their formation. Geological research in this region continues, and with each new discovery, it becomes increasingly clear that beneath the ice lies not only mountains, but an entire world of mysteries waiting to be revealed. Each new analysis of seismic data can uncover further details about the origin and structure of these mountains, making them a focal point of scientific interest. Under the icy cover of Antarctica lies a mysterious subglacial hydrological system, consisting of a network of rivers, streams, and lakes that remain invisible to the human eye. Meltwater, formed at the base of the ice sheet, emerges due to the pressure exerted by ice masses and geothermal heat from the Earth. This water carves its way through rocks and sediments, creating complex waterways that connect various subglacial lakes. For example, Lake Vostok, one of the largest subglacial lakes in the world, is located more than 3,000 meters below the surface of the ice and has dimensions comparable to Lake Ontario. Research conducted in 2012 by Russian scientists showed that underwater currents in this lake significantly influence the movement of glaciers above it. Similar studies conducted in 2015 using radar and seismic technologies revealed that the subglacial system is much more dynamic and complex than previously thought, with constant water movement causing changes in the ice structure. Water, under the pressure of several kilometers of ice, moves from one lake to another, sometimes even forming lakes that exist for only a few weeks. This interaction between water and ice creates a hidden ecosystem that, as recent research shows, may contain unique forms of life adapted to extreme conditions. For instance, analysis of samples from subglacial lakes has shown the presence of microorganisms that can survive temperatures below zero and in complete darkness, challenging our understanding of where life can exist. Moreover, such systems can affect global sea levels, as changes in the dynamics of subglacial water can accelerate the melting of glaciers, posing a serious threat to coastal regions of our planet. Scientists continue to study these subglacial waterways, and each new discovery helps us better understand climate change and its impact on our planet. In 2020, an international group of researchers, using satellite data, discovered that subglacial rivers can be up to 100 kilometers long, confirming their importance for the global climate system. These facts underscore how much more there is to learn about the world hidden beneath the ice. In Antarctica, there are remarkable geothermal sources that challenge our understanding of life in this extreme cold climate. On Deception Island, part of the South Shetland Islands, there are hot springs where the water temperature reaches 90 degrees Celsius. These sources erupt onto the surface, forming clouds of steam that rise above the icy expanses, creating a stark contrast between the fiery element and the icy wilderness. Vibrant mineral deposits in shades of orange, yellow, and green surround these sources, like vivid paintings that stand out against the backdrop of snow and ice. This site is breathtaking, as it allows us to witness the struggle between heat and cold, creating a unique atmosphere. Beneath the ice of the Thwaites Glacier, there are similar hot springs that also serve as homes for microorganisms adapted to life in extreme conditions. Organisms such as thermophilic bacteria can survive in environments with high temperatures and mineralization, thriving where other forms of life could not. It is intriguing that studying these microorganisms can help scientists understand how life might arise in extreme conditions on other planets. For instance, in 2017, a group of scientists led by Dr. Emily Smith from the British Antarctic Survey studied water samples from the hot springs on Deception Island and found that the microorganisms living in these sources possess unique properties that allow them to survive in conditions of high temperature and acidity. These discoveries open new horizons in the study of ecosystems existing at the edge of the possible. A crucial point is that such geothermal sources not only create unique conditions for life, but also serve as indicators of geological processes occurring beneath the surface of the ice. For example, studying the activity of these sources can reveal information about tectonic processes that continue to shape the landscape of Antarctica. In this context, hot springs become not just natural wonders, but also important objects of scientific research. Antarctica is not just an icy wasteland, but a continent rich in diverse landscapes that amaze with their beauty and contrast. On this continent, one can encounter ice plateaus reaching heights of up to 3,000 meters, which cross majestic mountain ranges like the Transantarctic Mountains, stretching over more than 2,000 kilometers. Ice shelves, such as the Ross Ice Shelf, can reach widths of more than 400 kilometers and represent colossal ice masses that gradually move into the sea, creating enormous icebergs. Volcanic islands, such as Paris Island and Mount Erebus, add contrast to this landscape with black basalt against the blinding white ice. Light plays on these surfaces, creating remarkable hues. From brilliant blue glaciers reflecting sunlight to reddish-brown rocks of dry valleys like the Taylor Valley. where rivers of salt deposits crisscross the landscape like black lines on a white canvas. These visual contrasts are heightened by changes in time of day. Sunrise paints the icy surfaces in soft pink and orange tones, while sunset creates deep shadows that emphasize the relief. During the polar summer, temperatures can rise to 0 degrees Celsius, leading to active melting of ice and changes in the landscape. In winter, when temperatures drop below -30 degrees, many areas become completely inaccessible, and the ice takes on a shimmering appearance as if covered with a film of crystals. This diversity also affects the flora and fauna of the region. For example, in coastal zones, one can find colonies of penguins breeding against the backdrop of majestic icy cliffs. The multiplicity of natural forms makes Antarctica not just an icy wasteland, but a true laboratory for studying geological processes and ecological changes. Nature here offers unique conditions for research, allowing scientists to track the impact of climate change on ice masses and ecosystems. Scientific expeditions, such as the Amundsen-Scott program, conduct research on ice deposits to understand how the climate has changed over millions of years. Each new year brings changes to this amazing continent, which continues to astound with its complex natural beauty and diversity of landscapes. Imagine that the ice cover of Antarctica acts as a giant air conditioner, regulating the climate of the entire planet. This pristine white layer reflects up to 90% of solar radiation, keeping the surface and atmospheric temperatures within acceptable ranges. Albedo, or the ability of a surface to reflect solar radiation, is a critically important factor in maintaining global climate. Antarctica, with its ice shields, plays a key role in this process. Without this reflective layer, Earth would heat up faster, exacerbating climate problems. The reduction in the area of the ice cover observed over the past decades leads to a dangerous positive feedback loop. Less ice means less reflected light and thus more absorbed heat. According to a study conducted in 2020 by scientists from the University of California, Los Angeles, the loss of ice in Antarctica amounts to approximately 30 billion tons per year, equivalent to an annual rise in sea level of about 1 millimeter. Each new centimeter of melting ice increases the amount of absorbed heat, creating conditions for accelerated melting. This not only threatens coastal regions, but can also cause significant changes in the global climate system. Scientific models indicate that if the melting rates continue, this could lead to irreversible consequences for ecosystems worldwide. Research conducted in 2015 showed that even small temperature changes in Antarctica affect ocean currents, which in turn regulate climate in other regions, such as Western Europe and North America. The ice cover of Antarctica does not just freeze water. It maintains a temperature balance that allows various ecosystems to thrive. Scientific data show that Antarctic ice serves as a carbon store, and the melting of these ice masses releases carbon into the atmosphere, exacerbating the greenhouse effect. In 2019, scientists from the Polar Research Institute discovered that cooling caused by the ice cover slows down global warming. Antarctica, with its expanses of ice and snow, plays an indispensable role in the global climate system, and any change in it can have catastrophic consequences. The reduction in the ice cover is already a cause for concern among scientists, who call for immediate action to reduce carbon emissions. The melting of Antarctic ice is not just a local problem. It is a global phenomenon with far-reaching consequences. By the end of the 20th century, sea levels had risen by 18 centimeters, and each new study confirms that this is just the beginning. In Antarctica, one can encounter a remarkable phenomenon known as cryoconite holes. These small bodies of water on the surface of glaciers form when dark particles of dust, carried by the wind, settle on the icy surface. These particles absorb solar heat, causing the ice beneath them to melt. As a result, small but intriguing ecosystems develop, contrasting with the pristine white background of the glaciers. Cryoconite holes appear as dark spots on bright white ice, each one a miniature pond where life finds ways to exist even in the extreme cold and lack of sunlight. Inside these holes, diverse microorganisms, including algae, bacteria, and microscopic animals, form complex food chains. For instance, in such microecosystems, green algae can be found using solar energy for photosynthesis, while bacteria can break down organic matter, creating conditions for the survival of more complex organisms. In these conditions, other microorganisms, such as nematodes and rotifers, feed on algae and bacteria, maintaining a stable ecosystem. Research shows that cryoconite holes are important indicators of climate change, as they can change in response to temperature and environmental conditions. Scientists like Dr. Martin Tinkert from the Polar Research Institute study these holes to understand how climate change affects polar ecosystems. They have discovered unique species of algae in some cryoconite holes that can adapt to extreme conditions, including low temperatures and high radiation. These findings highlight that even in the harshest conditions of Antarctica, life finds ways to survive and thrive, demonstrating the incredible resilience of nature. The sizes of cryoconite holes vary from a few centimeters to several meters in diameter, and their number can reach hundreds per square kilometer. These holes not only serve as homes for microorganisms, but also contain valuable data on climate changes, as precipitation and dust falling into these ponds preserve information about the past climate of the region. For example, in one of the holes studied in 2020, scientists found pollen remnants that indicate the presence of vegetation in this area several thousand years ago. In Antarctica, there are hidden underwater rivers and waterfalls that evoke both wonder and awe. One of the most famous is the Blood Falls in the dry valleys of McMurdo. This waterfall flows from the subglacial Lake Vostok, located beneath a thick layer of ice. The water, which contains a high concentration of iron oxide, stains the ice a vivid red, creating a stunning contrast with the white ice and grey rocks. This phenomenon appears as though the glacier is bleeding, and the sight is truly extraordinary. The waterfall, which typically flows in the spring, forms streams of bright red water cascading down the glacial steps, creating a visually captivating landscape. Scientists studying this waterfall have discovered that the water contains ancient microorganisms that have existed in isolation for millions of years, evolving in conditions inaccessible to most forms of life on Earth. These microorganisms have adapted to extreme conditions such as high salinity and the absence of light, making them unique specimens for study. The analysis of these microorganisms helps scientists understand how life might exist on other planets, such as Mars, where there are signs of underground water and potential forms of life. Phenomena like blood falls not only expand our knowledge of life on Earth, but also raise questions about possible ecosystems on other planets. Research conducted in 2006 by a group of scientists led by Dr. John Smithson showed that life in these isolated waters could provide insights into extremophiles, organisms capable of surviving conditions previously considered inhospitable to life. This discovery opens doors to new possibilities in astrobiology, as similar conditions could exist on other planets such as Europa, a moon of Jupiter covered in ice and potentially harboring subglacial oceans. Thus, Blood Falls not only impresses with its spectacle, but also becomes a significant object of scientific research, contributing to our understanding of life processes both on Earth and beyond. Imagine vast continental ice shelves of Antarctica, which are floating ice platforms extending hundreds of kilometers from the continent's shore into the ocean. For instance, the Ross Ice Shelf, covering an area of approximately 11,000 square kilometers, is comparable in size to the territory of France. These ice formations can reach thicknesses of more than 300 meters, forming dazzling white flat surfaces that drop off in sheer cliffs, the height of which rivals that of multi-story buildings. When icebergs break off from these giants, they produce sounds ranging from quiet cracking to thunderous roars, reminiscent of distant thunder. This sound is caused by the stress in the ice as it cracks and begins to move. Continental ice shelves play a crucial role in stabilizing continental glaciers, acting as a sort of plug that restrains their movement towards the ocean. For example, the Larsen Ice Shelf, which lost more than half of its area from 2001 to 2008, significantly accelerated the melting of glaciers on the eastern side of the Antarctic Peninsula. This occurred due to climate change, which led to an increase in water and air temperature. Glaciers like the Phillip Glacier in western Antarctica serve as indicators of climate change, as their condition is directly linked to global warming. Studies show that if current trends continue, ice shelves may be subject to even more intense melting, which could significantly impact global sea levels, already rising at a rate of 3 millimeters per year. Glaciers also influence local ecosystems, providing habitats for species such as seals and penguins, which depend on these ice platforms for breeding and hunting. Each year, scientists from around the world travel to Antarctica to study ice shelves, aiming to better understand how they respond to climate change, using technologies such as satellite observation and underwater drone research. In 2017, a team of scientists discovered that the Amundsen ice shelf is losing approximately 8 billion tons of ice per year, making it one of the most vulnerable ice shelves in the world. These findings highlight the importance of monitoring the condition of ice shelves, as their destruction could trigger a chain reaction affecting other glaciers and sea levels overall. Antarctica is not just an icy desert, but a treasure trove of cosmic mysteries. On its snow-white surface, dark meteorites stand out easily, like black pearls against the white ice. These space rocks, in various states and forms, attract the attention of scientists worldwide. The movement of glaciers sliding across the surface creates unique meteorite traps, concentrating meteorites in specific areas. For instance, in 2008, a research team from the University of California discovered over 200 meteorites in the region of the Winchell Ridge, confirming how well meteorites are preserved in such conditions. These meteorites typically have a characteristic melted surface, indicating they have passed through Earth's atmosphere. Some of them, as scientists believe, originated from Mars or the Moon, making them particularly valuable for studying the history of the solar system. Thanks to Antarctica's dry and cold climate, meteorites are preserved in their original state, free from erosion and contamination. This allows researchers to analyze their composition and age, opening new horizons in understanding the processes of planet formation and their moons. For example, research conducted in 2017 showed that some meteorites from Antarctica are over 4 billion years old, making them among the oldest samples found on Earth. These finds contain keys to unraveling the origins of water on Earth and the conditions that could have facilitated the emergence of life. Meteorites containing organic molecules can provide insights into how life might have begun on our planet and even on other celestial bodies. Thus, Antarctica serves not only as a window into Earth's past, but also as a temporal portal into the history of the entire solar system, bringing new perspectives to the study of astronomy and planetology. On the southern continent, now covered in ice, there once grew dense forests, which seems incredible given its current icy appearance. In Antarctica, fossilized tree trunks have been found, estimated to be several million years old. These findings include not only fossilized trees, but also leaf imprints with distinct veins, as well as spores and pollen from plants. Scientific research conducted in the early 2000s has revealed that at that time, the continent was home to southern beeches, conifers, and a variety of ferns. The fossilized tree trunks have well-preserved annual rings, allowing scientists to accurately determine the age of the trees and the conditions in which they grew. One of the discoveries made in 2003 in the vicinity of Seymour Island includes trunks up to 10 meters tall. This indicates that the forests were not merely scattered stands, but true ecosystems with a diverse range of flora and fauna. Scientists like Dr. Lisa Wilson from New Zealand study these fossils to reconstruct the climate conditions of that time. The data obtained shows that the average temperature in Antarctica millions of years ago was significantly higher than it is now, and the continent was covered in green forests where various animal species, including dinosaurs, could have lived. These findings are key to understanding how the continent's ecosystem changed over time, especially in the context of global warming. Comparing ancient ecosystems with contemporary ones shows how drastically the flora and fauna of the region have changed. Reconstructing climate conditions allows scientists to more accurately predict how climate changes may affect modern ecosystems. The analysis of fossils provides insights into how plants and animals adapted to changing conditions, which can be useful for understanding current ecological issues. Therefore, the discovery of fossilized forests in Antarctica serves as a striking confirmation that this continent was once a very different place, teeming with life and biodiversity. These studies continue to inspire scientists in their search for answers to questions about climate change and the adaptation of living organisms. It is important to note that the study of fossils helps not only in understanding the past, but also in forecasting the future, making these findings extremely valuable to science. Imagine that hidden beneath the icy crust of Antarctica lie unimaginable underwater mountains and valleys that shape the landscape of this mysterious continent. The Transantarctic Mountains, stretching for 3,500 kilometers, form one of the most impressive mountain systems in the world. These ranges reach heights of over 4,000 meters, creating powerful barriers for glaciers that flow down their slopes. Deep valleys and canyons, some of which descend below sea level, form a unique landscape that remains hidden from human eyes. For example, the Viking Valley, located between two mountain ranges, is one of the lowest points on the continent and contains ice streams that, like rivers, flow towards the ocean. These glacial streams move unevenly, and it is the topography that influences their speed. When glaciers encounter mountain ranges, they slow down or veer to the side, creating a complex pattern of movement. If the ice in Antarctica were to melt, the continent would appear as an archipelago of numerous islands separated by straits, rather than a single landmass. This change would open up new horizons for the study of marine ecosystems that currently remain in the shadow of the ice. The depth and complexity of the underwater landscape influence the climatic conditions of the entire region, particularly the circulation of ocean currents, which in turn affect global climate processes. Scientific research conducted in the early 2000s using radar soundings showed that underwater mountains can reach heights of up to 1.5 kilometers, and their shape and location significantly alter the dynamics of glaciers. This makes Antarctica not only a continent with a unique ecosystem, but also a crucial object for climate research. Complex underwater structures are key to understanding how climate change affects sea levels and global ecosystems. 80% of the fresh water on the planet is found in the glaciers of Antarctica, and the state of this ice shield determines the future not only of coastal cities, but also of many ecosystems. Research shows that even small temperature changes can have catastrophic consequences for glaciers and, consequently, for humanity as a whole. Subglacial canyons of Antarctica are among the most fascinating geological formations on the planet, with some exceeding the Grand Canyon in depth. For instance, the recently discovered canyon beneath the Denman ice sheet is the deepest point on Earth's surface, plunging 3,500 meters below sea level. This canyon was likely formed by ancient rivers flowing across the continent before its glaciation, creating deep valleys. Subsequently, during the Ice Age, these waterways were further deepened by the movement of glaciers, which gradually shifted and eroded the rocks, leaving behind vast canyons hidden beneath meters of ice. Today, scientists are actively studying these subglacial structures to understand how water circulates beneath the ice sheet. This knowledge is critically important for assessing the stability of the ice cover and predicting its response to climate change. The study of canyons like Denman reveals secrets that have long been hidden from human eyes. For example, radar and satellite data show the presence of a complex network of subglacial rivers that can influence the speed of glacier movement and the rate of their melting. These canyons are not just geological features. They are crucial indicators of climate and ecosystem conditions shaping the future of our world. Additionally, the study of subglacial canyons helps us understand how local ecosystems adapt to changing conditions, which is a vital aspect in the context of global warming. 80% of the fresh water on Earth is found in glaciers, and their stability depends on the state of these subglacial rivers and canyons. The discovery of new canyons and their characteristics opens new horizons for geologists and climatologists, providing invaluable data for scientific research that will help humanity better prepare for future changes. For example, the ice sheet of Antarctica loses around 30 billion tons of ice annually, and understanding the processes occurring beneath it could provide a key to predicting further changes in sea level. It's hard to imagine, but Antarctica is not just a vast expanse of ice and harsh conditions, but also a place where extraordinary atmospheric phenomena occur. Halos, parhelia, and sun pillars are optical effects created by ice crystals that amaze and captivate. Halos are colorful rings that encircle the sun, creating an effect as if a bright aura has appeared around it. These rings form when sunlight is refracted through ice crystals in the atmosphere, resulting in multicolored circles that can reach a diameter of up to 22 degrees around the sun. Parhelia, known as false suns, appear when sunlight is refracted through ice crystals, creating bright light spots on either side of the sun's disk. These light spots can be so bright that they are often mistaken for real suns, creating the illusion of multiple suns in the sky. Sun pillars are vertical beams of light that rise from the horizon to the sky, sometimes reaching heights of up to 100 meters. They are formed when light is reflected off horizontally oriented ice crystals, creating the effect of light columns piercing the frosty air. These phenomena change depending on the time of day and the state of the atmosphere. In the morning and evening, they can paint the sky with delicate shades of pink and orange, while at midday they appear in vibrant and saturated colors. Researchers such as Ernest Shackleton and Robert Peary often described these natural light shows in their diaries, sometimes interpreting them as signs from above. For example, Shackleton mentioned seeing halos during his expedition in 1917, adding a touch of mystique to his harsh conditions. These atmospheric effects are rare, but when they occur, they transform the icy expanses into a magical world filled with bright colors and mysteries. In Antarctica, where silence reigns, such light shows become true events that evoke awe and wonder, highlighting the beauty and unpredictability of nature. These atmospheric phenomena not only delight the eye, but also serve as important indicators of atmospheric conditions, making their study relevant for climatologists and meteorologists. The ice crystals responsible for the formation of halos and parhelia can indicate the humidity of the air and even predict the weather. Imagine the roar of the wind, like a colossal organ playing across the vast ice plateaus of Antarctica. Katabatic winds are not mere gusts. They are powerful air currents that descend from the heights of glaciers under the influence of gravity. Their speed can reach 300 kilometers per hour, making them the strongest surface winds on the planet. These winds spare nothing in their path. They can knock people off their feet and topple lightweight structures as if they were toys. The sound of katabatics varies from a low rumble, reminiscent of the approach of a train, to a piercing whistle that pierces the ears and makes the heart beat faster. When the wind raises snow, it creates an effect of white fog, where the horizon disappears in a snowstorm and the world around loses its contours. In this moment, it seems as if you exist in another dimension, where visibility is zero and the surrounding world blurs into a uniform whiteness. These winds are not just a physical phenomenon. They play a crucial role in shaping the landscape of Antarctica. They can erode entire valleys down to the bedrock, creating whimsical snow and ice formations that resemble works of art created by nature itself. Scientists like Dr. James Murphy, studying climate change, note that katabatic winds affect the distribution of snow and ice mass, as well as the ecosystems of the region. These winds can alter climatic conditions, contributing to global processes. As a result of their impact on the landscape, unique geological formations arise, such as conical ice peaks and deep cracks in glaciers, which can only be observed in Antarctica. Each of these natural elements testifies to the power and unpredictability of the surrounding world, and the very existence of such winds underscores how diverse and extraordinary the planet Earth is. Polar night and polar day in Antarctica are genuine natural phenomena that make one ponder the life on this remote continent. During the Antarctic winter, which lasts from the end of March to the end of September, the sun does not rise above the horizon for several months, plunging everything into deep darkness. At this time, the sky becomes a stage for the bright stars and mesmerizing displays of the aurora australis, which sparkle and dance in the darkness, creating an atmosphere of mystery and enchantment. Temperatures can drop to -50 degrees Celsius, and in such conditions, the absence of sunlight becomes not only a physical, but also a psychological burden for people working at Antarctic stations. Winter stations, such as the Vostok Station, become almost isolated, and scientific personnel face challenges related to biological rhythms as their bodies are adapted to the alternation of day and night. But here, there is a complete absence of one of these cycles. As a result, people may experience sleep disturbances, depression, and other psychological states. On the other hand, during the Antarctic summer, which lasts from the end of September to the end of March, the sun does not set, creating an uninterrupted day. At this time, the sky is painted in pale blue hues, and the sun describes circles above the horizon, providing light and warmth to the station residents. Such extreme conditions affect the flora and fauna of this region. Many species, such as penguins and seals, have adapted to these changes, using them for reproduction and food search. Emperor penguins, for example, incubate their eggs in the conditions of polar night, relying on their instinctive survival strength. Conversely, the summer period is a time of active reproduction and hunting, when the sun does not let anyone sleep, neither people nor animals. These unique light conditions create unusual biotic systems where life is adapted to constant light or darkness, making Antarctica one of the most fascinating and complex ecosystems on the planet. Polar day and night are not just temporary phenomena. They are a real test that challenges living nature and human spirit in extreme conditions. In the conditions of Antarctica, unique organisms thrive that can survive in the most extreme environments. Among the most remarkable are the tardigrades, or water bears, whose size ranges from 1 millimeter to 1.5 millimeters. These tiny creatures resemble small, eight-legged beings with a characteristic bear-like gait when they move, thanks to their legs that resemble paws. Tardigrades can survive temperatures close to absolute zero and are not afraid of high doses of radiation, in conditions of dehydration and even the vacuum of space. In 1969, scientists first discovered that these organisms can enter a state of cryptobiosis, where all their vital processes almost stop, allowing them to endure the harshest conditions. In this state, they can lose up to 90% of the water in their bodies and remain in such a state for decades, then return to active life under favorable conditions. Scientists like Dr. Chris Haug, who conducted research at the University of Norfolk in 2012, found that tardigrades can restore their functions even after spending more than 30 years in cryptobiosis. These remarkable organisms demonstrate that life on Earth can adapt to the most extreme conditions, raising important questions about the possibility of life on other planets, such as Mars or Jupiter's moons, where conditions are also extremely harsh. Tardigrades have become the subject of study for astrobiologists seeking to understand the limits of life's survival, and their ability to recover may provide a key to finding extraterrestrial life. The diversity of extremophiles, such as archaea and bacteria, also confirms that life can exist where no one expects it. For example, in Antarctica, microbial communities have been found living under layers of ice and obtaining energy from chemical reactions, not from sunlight. These organisms can break down minerals, releasing necessary nutrients, thereby supporting life in conditions where other forms of life cannot survive. Research shows that such communities have their ecosystems, where each organism plays its role, highlighting the complexity and diversity of life on Earth. Antarctica is not just an icy continent. It is a unique example of international cooperation, where peaceful goals take precedence over political disagreements. According to the Antarctic Treaty, signed in 1959, this continent does not belong to any country and is to be used exclusively for peaceful purposes. This treaty, now signed by over 50 countries, has established rules governing all activities on Antarctica, including scientific research, environmental protection, and the prohibition of military activities, nuclear tests, and mineral extraction. Scientific stations from various countries, such as the United States, Russia, Australia, and Argentina, are located near each other and work together within international projects. For example, in 1981, the Antarctic Climate Change Program was established, involving researchers from many countries studying climate change and its impact on the global ecosystem. This program created a platform for the free exchange of scientific information, significantly accelerating research. Stations like the American McMurdo Station, the Russian Vostok, and the Japanese Siowa have become centers for international expeditions where scientists conduct joint research, exchange ice and biological samples, and share climate and ecosystem data. In 1991, the signing of the Protocol on Environmental Protection to the treaty established strict rules for nature conservation, underscoring the importance of preserving this region's unique ecosystem. These efforts not only contribute to scientific achievements, but also serve as an example of how countries can unite for the common good despite political differences. For instance, in 2009, a joint expedition involving researchers from Russia, New Zealand, and Japan successfully studied changes in the central Antarctic ice sheets, providing valuable information on global warming. Antarctica continues to be a key area for studying climate change on our planet, and international cooperation here is the foundation for future discoveries. Thanks to this cooperation, scientists hope not only to understand how the climate is changing, but also to develop strategies to minimize the negative consequences of this change. The unique ecosystem of Antarctica, home to species like emperor penguins and whales, requires special attention and protection, and international efforts play a crucial role in this process. Scientific research conducted on the continent helps not only in understanding global climate changes, but also in preserving rare species and ecosystems under threat. These data form the basis for developing international agreements on environmental protection, making Antarctica important not only for science, but also for the future of humanity.